Okay, our new topic is capacitors, and capacitors is just another electrical component. And what it consists of is essentially two metal plates with an insulator in between. And what that allows the capacitor to do is to store charge. Okay, so um, if we put a capacitor in a circuit with a power supply, so let's just have a cell here, positive side, negative side. And our symbol for a capacitor is just two parallel lines. Okay, it just represents really the two metal plates. Now initially there'll be no charge in the capacitor, but what happens is this voltage, the EMF from our supply, will push current around the circuit. And if we think of it in terms of electrons at first, what will happen is the electrons that are here in this wire will get pushed by our power supply onto this plate of the capacitor, okay, which will make that plate negatively charged. However, the other plate can feel the repulsion from all those electrons when they build up a negative charge there. So what happens is electrons leave that plate and will kind of travel around the circle like this. And we're left with a positive charge because that plate has lost negative electrons. There'll still be positive protons there. So essentially what we end up with, without drawing all the electrons, is our capacitor has a buildup of negative charge on the plate that was connected to the negative side of the cell, and a buildup of positive charge on the plate that was connected to the positive side of the cell. So our capacitor will store charge, but there's also energy stored there, and that's essentially the two things that capacitors are used for in a circuit. Now, this cell will continue to try and push electrons around like this with, say, a voltage of, I don't know, 5 volts. But eventually what happens is, as the charge builds up on this capacitor, all those electrons that are on this plate here will repel each other, so there's a push really back against it. And as long as this push is bigger than the push on the capacitor, more electrons will continue to build up on our capacitor. So our capacitor will keep gaining charge until such a time as the voltage here cancels out the voltage here. So essentially the push from our cell, our power supply, is cancelled out by the electrostatic repulsion of the buildup of charge on the capacitor, and then it balances out. And at that stage we would say the capacitor is fully charged. Okay. Now the amount of charge that can be pushed onto a capacitor depends on two things. The voltage, so if we were to raise the voltage up here, there'd be a bigger push and we could push more charge onto the capacitor. The other thing that affects it is the size of the capacitor. And really by the size of the capacitor, we're talking not something we can measure in meters or anything like that, but it's something we measure in farads, and it really just gives an idea of the capacity of the capacitor, and we call that the capacitance. Okay, so we have an equation which is that C equals QV. This is an equation you will use a lot through this unit and in your exams. So Q we've come across before is the charge stored in coulombs. Coulombs C, so the unit of charge is measured in coulombs, capital C. Voltage is the potential difference across the capacitor, which is measured in volts V. And this is why we couldn't use C for current or C for charge, because C is used in electronics as the capacitance of the capacitor, but that is measured in farads, F. And to be honest, a 1 farad capacitor would be huge. So most of the time we're going to be dealing with either millifarads or possibly micro or nano farads. Okay, 1 farad is quite a large unit. What does 1 farad mean? Well, if we just look at that equation, 1 farad, if we look at our C in the capacitance, would mean 1 coulomb of charge for every volt across it. Okay, so really 1 farad, or farad, is the amount of charge per unit volt across it. So let's look at an example. So it says a capacitor stores, so that's the Q, 3 coulombs of charge when a voltage of 5 volts is put across it, calculate the capacitance. So, I mean, you can learn the equation off like this. I think most people probably learn off as Q equals CV. And we can put the values in like that. So C would equal 3 over 5, which is 0.6. And remember, it's capacitance, which is measured in farads. The second one then, the charge stored when a PD of 1.5 volts is applied. Now that capacitance we worked out is a property, i.e. it's a constant of that capacitor in that circuit. So we can use what we worked out in part 1 for part 2. The voltage is now 1.5 volts and we're trying to find Q. So we do Q equals CV, Q equals 0.6 times 1.5. So Q is equal to 0.9 and Q is charge, which is coulombs, capital C. Okay, so try the questions below, show you're working out, and see if you get the same answers that are written in this OneNote.